In activity 1.21, we are given the local linearization for some function y equals g of x, but not the actual function. So let's see what we can figure out just knowing the local linearization about the original function. Well, first part, A, asks us to compute L of -1 and L prime of -1. So these are going to be using the local linearization. L of -1 is very straightforward. We're just plugging -1 in here and calculating, and you'll see this will be 0, so it just comes out to be -2. L prime of -1, we can calculate that without really doing any work, because remember, this line is linear. Linear has a constant rate of change, so the derivative is the same everywhere, and in fact it's equal to the slope, which is 3. So we can do it without actually having to calculate the derivative. Part B is very similar. It's asking us to find g of -1 and g prime of -1. Well, interestingly enough, we've already done the work for this, because the local linearization of a function, or the tangent line of a function, shares the same y value and slope at the point of tangency, which is -1. So at -1, g needs to have the same function value, so g of -1 has to be -2, and g has to have the same slope, so g prime of -1 is 3. So this is a property of all tangent lines. Now part C, they ask us about g of -1.03, and we want to know if it's going to be bigger or smaller than g of -1. Well, notice that at -1, we're told that g has a slope of 3. That means at -1, g is an increasing function. So, because g is an increasing function, as the inputs go up, the outputs should go up. So we should assume that g of -1 will be larger than g of -1.3. Again, because g is increasing. And we know that because g is increasing at let's be specific, at a equals -1. We know that because g prime of -1 is 3. It's positive. D, we could use our local linearization to calculate g of -1.03. It's going to be approximately our tangent line evaluated at -1.03. So plugging that into our tangent line, so -2 plus 3 times -1.03 plus 1, we get that that is equal to -2.09 if you calculate that out. Now just one thing I want to point out. Notice here I use the squiggly equals because this is an approximation of the function value. But here I just use regular equals because L of -1.03 is equal to this exactly, which is exactly equal to -2.09. And notice what we find. -2.09 is smaller than -2, which was our g of -1, which is what we were asked in part C. So we're verifying what we saw in part C. E, if we also knew that g double prime of -1 equals 2, well, think about what that tells us about the graph. That tells us that the graph of g is concave up from our study of second derivatives at a equals -1. So that means at -1, not only is the function increasing, but it's got an increasing rate of change. Now, let's go ahead and sketch what's going on in our graph. So, I'm going to make each one every 2 to be 1. So this will be 1, 1, 1, -1, sorry, -1 here, -2, -2. So let's sketch our local linearization first, because we can do that exactly. Now, what do we know? Well, we said that this function is going to go through the point -1, -2. So that's right here. Now, both the tangent line and the original function will go through this point. Now the tangent line is going to be a linear function. It has a slope of 3, so let's plot one more point. We go up 1, 2, 3, and over 1. So we can now draw our tangent line here between those 2 points. So that is the graph of L of x. Now, we wanted to try and get an idea of what our original function is looking like. Well, we only know what's going on around our point of tangency. And what do we know? Well, we know it shares this point, it shares this slope, and also that the second derivative was positive, so it needs to be concave up. So it's going to sit above our tangent line. So one possibility is it might look like this around -1. Now, because we just did a local linearization, we don't know what else is going on after that. For instance, our graph may come back over and do something like this over here. It may come back up over here. We don't know. We don't have enough information, but we know that around -1, if we were to zoom in on that point, it's going to look something like that, where it sits on top of our tangent line because it's concave up.